Heat engines are devices which undergo cyclic processes, converting heat energy to work. The system, in the case of a heat engine, is known as the working substance. In an internal combustion engine, the working substance is the fuel-air mixture, while it is steam in case of a steam engine. The working substance undergoes several processes in a cycle. In some of these processes, it absorbs heat Q1 from an external reservoir at high temperature T1, while in some other processes, it releases heat Q2 into an external reservoir at temperature T2. The work done by the system W is transferred to the surroundings by means of some mechanical arrangement like a piston. Schematically, this can be shown as above. This cycle is repeated again and again to derive useful work. The efficiency of a heat engine eta is given by eta equals W by Q1. Q1 is the heat input to the system, while W is the work done by it in one cycle. In a complete cycle, some amount of heat is also rejected to the surroundings. Then, over one complete cycle, the work done is W equals Q1 minus Q2. Therefore, eta equals 1 minus Q2 by Q1.
For Q2 equals 0, eta equals 1. The engine would be converting heat into work at 100% efficiency. Though theoretically the first law of thermodynamics approves of such a possibility, it can be considered practically impossible to have such an ideal engine with eta equals 1. Energy losses are inevitable and they can only be minimized. As it turns out that the efficiency of any heat engine has a fundamental limit set by another natural law, namely the second law of thermodynamics. The mechanism of conversion of heat into work varies for different heat engines. There are two basic ways. Either the system is heated externally by a furnace, like in the case of steam engines, or the system is heated internally by exothermic chemical reactions, like in an internal combustion engine. The steps involved may also differ from engine to engine.